Hello? Can you hear me? No? Okay, great. So, categorical local Langlands. Some version. So let's again just as before. So why it's always way. Huh? It's always okay. G over F. Let's say quasi split. Before reductive. Just fix some notations before. F is non-accumulating local field. Residual characteristic P. And we sort of fix some opinion for real. And I usually denote by E from the unipotent radical U to GA, some which is such as restriction to every simple root subspace is isomorphism and the psi additive character. Some coefficient, I will also fix this lambda some coefficient ring, which will be over some over ZL QL or FL, which is some algebraic extension, but lambda will be regular Noetherian ring at some point, maybe DVR. Fix something like that. Added non-trivial additive character. So the goal of this series of lectures is I'm going to explain the following thing. First one is try to explain the following theorem, give an idea. There exists canonical equivalence depending on the choice of the pin is fixed. I will never change that, but the remaining things depends on the choices psi from maybe at Tame from the category of some version introduced already mentioned last week, some so-called shifts on ISOC, but at Tame part, this is equivalent to the category of incoherent shift on the stack of parameters, which was introduced last week, the last talk, but I'll prefer to write this log of GL over lambda. Here, this is lambda is, let's say, QL bar, first thing. I mean, you're afraid to write the par G, as what happens in all the other talks. Just for me, par sometimes looks like parabolic, so I sort of like to use log. Tame, also there's Tame. So I think the Tame part on the spectral set, stack of Tame Langlands parameter on the spectral set was explained last week. I will try to explain what the Tame on the left-hand side later on, maybe next lecture. And the second goal is to when explain some version for arithmetic applications, explain something for lambda for FL coefficient, some version, which is going to sort of more subtle, I think. Even the formulation is more subtle, so I'll talk about that later. So I'm not going to try to do it now. Maybe the order may change, I guess. But there's some part of the thing I want to talk. We'll see how much at the end we'll get it. But the third is matching some objects. Actually, to have this to be useful in practice, mention some objects under this functor. So make it more concrete. It's not just an abstract equivalence. 4 is, I will try to, for me, one of the motivation to do this categorical version of local Langlands is try to deduce classical local Langlands from it, not go the other way around. And it hasn't been really achieved, I think. But I will try to do some supercuspidal parts, how to get some supercuspidal deduce supercuspidal, maybe Tame supercuspidal classical local Langlands. From this categorical version, try to deduce that. Maybe 5 is maybe some other applications. So these are kind of some applications. These are maybe some other applications. If I have time to talk about it. So that's roughly the goal. In fact, I don't know. There's already one application I could see now, if you assume the correspondence, assume exists in such correspondence, the theorem is, maybe I don't write it, but let me just mention it. In the last lecture, Lucas talked about this crucial theorem they need in this some finiteness of the coherence shifts of stack parameters. So actually, one can, of course, we will hear like a nice proof using this kind of geometric lemma this afternoon. I hope that's the plan, I guess. But there's also actually, if you already know the first equivalence, you can already deduce it kind of cheaply. The reason is once you know the equivalence tells you what happens on the Tame parts, and you can compute the home space of a coherent shift, translate to the computing home of compact objects on the stack of isocrystals or something like that. And there you will, after today's lecture, you will see the home space will be finite dimensional there. It's going to be, or bounded cohomological degree. Then there's a well-known procedure that all the other components of stack parameters are more or less like the Tame stack, up to some finiteness. There's some finite group. This is very subtle if you want to get real local Langlands correspondence reduced to general situation to Tame situation. There's some finite group involving very subtle, but for this finiteness question, like home space, the action of extra finite group doesn't really matter. So you will get the finiteness just I think from this equivalence from this one, just some kind of a cheap way to get it, but it doesn't really tell you anything about the geometry of the stack. So we will hear, I think, more about that. But I think there's some sort of kind of application of this kind that you could imagine. Some question in one side is hard, then you can translate to questions on the other hand, which on the other side, which can be computed very easily and go forth. So we will see whether we will get something there. All right, so that's kind of the plan for 6 lectures. Hopefully we'll cover at least some of them, if not all. Any questions so far? And then let me just see the strategy of one of proof of one is this is what we have heard in at some last week's lecture is by taking Frobenius twisted categorical trace of some tame local geometric Langlands. Okay, so this is just one sentence strategy to get this, and like in particular, like the unipotent part is basically this celebrated theorem of Bezukov-Nikov, and it's in equal characteristic, and which we heard last week, and then there's we also heard some talks by Arno about this what is the meaning of taking categorical trace. So basically, sort of combine this to get this. So proof of just get the equivalence is not that. I mean, the strategy is really straightforward. Actually, this idea of taking trace of Frobenius to get some Tame category, this local Langlands. The idea was already there for more than 10 years. You know, start to work on these things, it already appeared about 10 years ago, and it took some time to really first. Actually, at that time, even the formulation of categorical local Langlands hasn't been there yet, but there's some idea of air, and it took some time to really make everything work, make everything precise, and in particular work with some like this ISOC or some infinite dimensional geometrical object. It's kind of, you need the appropriate foundations to do that. So, that's the idea, and so today I'm gonna talk about some properties of this. I mean, not. Okay, there's also another lecture this afternoon, but maybe this morning, this lecture is properties of this one. Schiffer's isocrystals. One side of the categorical local Langlands, and I will talk about some properties. This was already introduced last week in Minja's talk, but I probably will get the because some people just came this week, so I very briefly recall what they are, and then talk about some properties. And I think maybe the next lecture I will be able to talk about what is this Tame part of this category, and then after that maybe we could get this equivalence. All right, so recall. So what is the ISO? So this is a stack of isocrystals, G isocrystals. On the puncture disk, D star, this is a spec of F. So what we do is, if you take the functor, so to make it precise, we take F is the algebraic closure of kappa bar, which kappa is a residual field. Let me just write this, just O more some variable. O is a ring of integers. It's a ring of integers. And then, so precisely, this is ISOC G. It's a functor. It's a so-called pre-stack. So it's basically a functor from the category of commutative K algebras, perfect K algebras, to the groupoid. Sends some ring R to E is pairs, E psi, where E is a G tosser on the puncture disk family version of parameterized by R, which is by definition spec of O WR, the ramified width vectors of R invert uniformizer pi. Okay, so let me just uniformizer pi. And phi is isomorphism from the forbidden. Then there's a forbiddenness on R. You can pull back. This is isomorphism. Okay, so that's a definition. In practice, we work with something slightly different, like, let me call Isaac et al. G to be those E phi such that the E is et al. Locally on R. Maybe right, it's like trivial. Meaning if you there's an et al. Cover of R such that this torsor become trivial. So it's not quite clear what at least for, I think it's not known yet whether every G torsor on like dr crosses can be trivialized over et al. Locally on R. So there's some slight difference. It's kind of subgroupoid, but it turns out it doesn't matter the remark. I will also review this sheaf, but the category of sheaves are equivalent. So it doesn't really matter in the statement which one we use. So this is in practice. Let's see. In practice. So the reason we want to use this et al. Version is this guy itself can be written as a loop group modulo the Frobenius conjugation by LG, where LG is a loop group. Oops. It's a loop group, so it's again the functor from the commutative K algebra to groupoids. Actually, in this is just a set, just sends R to G of W. Very pi. Okay. And then there's sigma is a Frobenius. So Frobenius endomorphism. Because these are functors defined over FP algebra, so there's a usual Frobenius. All right, okay. So that was the definition, and then we have this. So there's a shift theory, which I'm gonna briefly review after I state the theorem, and so then the theorem is the following. So let me just. Maybe before the theorem, let me just also review what Minja talked about last week. Is this guy itself? Oh, by the way, this was denoted by, I think, was denoted by B of G in Minja's talk. So let me just also remind you what was known is this guy itself. Admit has a you can add a tower knot. So I will at some point I probably will forget to add a tower, but it will be okay in either case. As a stratification. Indexed by a locally closed substack. B for B in BG, the Cartwright set. So each stack, this is a point. Each stack is actually has only one geometric point, but its automorphism is like is this per-finite group GBF, something like that. But this quotient you can understood properly either, for example, in Pro et al. Topology, or if you use isocrystal version, maybe in V topology or something like that. So this, and the important thing is it's not just stratified by locally closed stack, but actually this GB here inside the, okay, and this is a Cartwright set is it's a natural pose set, has a partial order, and then this natural minimal elements in there are usually called basic, and so every element, okay, this pose set has this property for every element. The subsets of elements less than or equal to it is finite and contains a unique minimal element, basically. And then for each B, you can consider what happens is, so okay, I also, you can just omit the G in the notation. So you have this, I should call this is I less than or equal to B. This composition is I of B. And this is, let me call this J. Maybe in my article I call J of B, but maybe like Ninas don't like it. Some other. So I just call it J because I'm going to use it at some point. Because JB might they need to refer it to in Fark-Schultz setting. It's a different. So okay, so let me just write in this way. The important thing is that this one is a finite presented, or maybe perfectly finite presented. Finitely presented close embedding. Closed embedding, and I of J is quasi-compact open embedding. Okay, so this is a basic structure. With quasi-compact open would also mean it's a finite presented embedding. All right, okay. That's so now let me just state the theorem. Okay, I still need to review what is this shift, but I will do it after I state this theorem. The theorem is as follows. So first one is this category is compactly generated. Second, there exists a canonical duality, self-duality. By the way, I think it was already mentioned last week, if a category is, okay, when we say in this, I think basically in this week, most time, when we say category, that would be mean presentable, stable, infinite category. And maybe it's linear over some coefficient, like this lambda in this case. But yeah, so here is lambda is arbitrary. Lambda is anything. This is over QL, FL, or ZL. And then last week, if you have a category is compact generated, then it's going to be automatically dualizable. But here is this is it's not just dualizable, but it's a self-duality. Which I denote by canonical. From the dual category to category itself, which of course it will such duality will automatically imply there's this duality of compact objects, which is something people more familiar with. And I think Arnold explained last week. If a category is compactly generated, then the compact objects of the dual category is just the opposite category of the compact objects of the original category. So this is this. And it also automatically implies something. Maybe I will talk that later. Really, very closely related to this admissible duality mentioned in a previous talk. From this sheets of so-called admissible thing, subcategory to up. So this admissible, so actually there's a general notion of admissible objects in a dualizable category. It's just sort of due to compact objects. And yeah, I can already give you, just see it, the definition, but I will probably talk more about this later on. One application, by the way, what's the definition of compact objects? An object in a category you can think about as a functor from the category of, let's say, lambda modules to this category. Continuous functor, yeah. You just then objects compact if this functor admits a continuous right adjoint. This is this, because commutable with compact. This is basically the definition, and the admissible objects is this functor admits a left adjoint. So it's completely due to compact objects, and so what happens is. Yeah, there's a canonic self-duality, and it automatically gives this two dualities, more familiar dualities on some subcategory of objects, and then it's going to be from the opposite category to the category itself. So there's, in other words, there's only one duality, not a bunch of different dualities. Dual categories, there's an intrinsic notion of a dualizable object in a symmetric monoidal category, which I think was explained last week in Arnold's talk.
Just a subcategory
No, in a symmetric monoidal category, you can, inside a symmetric monoidal category, given an object, you can ask whether it's dualizable or not. And if it is, then there's another object called the dual, right? Yeah, inside. It was explained, but in a very, if it's compactly generated, it actually, or not compactly generated, but in general, if it's dualizable, it's actually equivalent to the functor category from this shift of iso to the category of modules. Okay, it's you can think about functor categories. That's always the case. It's for example, it's a vector space. The category of vector space is dualizable if and only if it's finite dimensional, and in that case, its dual is home from that vector space to unit, one-dimensional vector space. Okay, so there's this self-duality. I think these two properties actually, for example, in the analog statements in the Fark-Schultz setting was also, I think, mentioned last week. At least compact generation was mentioned in Paul's talk or something. It's some pretty non-trivial result involves some geometry, I think. But here, in this content, it's a kind of actually more or less formal, I should say, once you set up the appropriate foundations. So I'm hoping to maybe give you some hint of how these are can be proved, at least so later on. But let me state the third part is there exists some like a Riemann or semi-orthogonal decomposition. So let me just write it. Yes. The third is there exists for any B. Every B, we have this. You can consider the closed subspace of basically the union of all the strata less than B. Then there's this functor I lower star, I upper star, and I upper shriek. Oops, sorry. I upper shriek. Go to shifts on the closed strata less than or equal to B, and go to this J upper star, upper shriek, which is same as upper star, and J lower shriek, J lower star. B, and all the functors preserve compact objects. Then 4 is if you look at just one strata, is okay? Just look at one strata. Because this strata is isomorphic to the classifying stack of the, some p-adic group, so actually the category is equivalent to the category of smooth representations of the p-adic groups, maybe. After you choose some point on the loop group preserve. What else? And also the fifth is this canonical duality. There's this if you take IB lower star, the push forward from the from the strata IB from here to ISOC. So there's a push forward, and then you push forward to then apply this canonical duality. Maybe the let's just think about compact part on compact objects. This will be the same as you first take some on the category of p-adic groups. There's this Bernstein Zielinski duality, and Bernstein called it the cohomological duality. So this is a BZ duality of category of smooth representations. Then what you can do is you always take this duality, then will be tensoring with some invertible sheaf on the or invertible, like one-dimensional representation up to shift of the p-adic group, then take the shriek extension of B. Yeah. Oops. Something like that. And this is some, let's see, one-dimensional, just a character of J up to shift, cohomological shift. So there was, in my original article, I was made a mistake to just say this CB is trivial. It was, I think, pointed out by Langlands, and maybe Xiang Qian also sort of realized it. Actually, it's non-trivial, and they have some suggestion how to compute it. Maybe I will see with later on this week. I will maybe give you the presentation or not. Let's see. what is so? Okay, so that's a statement of the theorem I want to discuss, and any questions so far?
So in part 3, you want to say that obtained
This is, I don't know, there's different terminology. I think in original BBDEG, they call it the recommend, and maybe some people call it semi-orthogonal decomposition. But there's more content. This is really preserve all compact objects. So actually, this part you can, maybe I just, this is a remark, is one can formally pass to, because it's preserved compact objects, their right adjoints are also continuous automatically. Pass to right adjoints. And to get the maybe semi-orthogonal decomposition, of so-called admissible objects. So I give the definition of admissible objects in any dualizable category, meaning the functor from category of, let's say, lambda module to it admits left adjoint. And if you use this definition, you will immediately see any right adjoint will preserve admissible objects. So it's completely formal. All right. So that's a statement of theorem. Any questions so far? Okay. So by the way, when did I start?
Maybe we have time until
12:05. Okay. Okay. All right. Okay. I should see there's maybe I give you some idea of proof some parts of the theorem, like part 1, 2. This is kind of also some kind of tutorial of how to think about this category of sheaves, this sheaf on this infinite dimensional space. This was introduced last week, this sheaf, this notion, but really how to work with it is kind of maybe not that familiar with for most people. So I maybe take this opportunity to explain part 1 and 2, that also gives you some idea how to work with this kind of shifts on this infinite dimensional vector space, infinite dimensional geometrical objects. Okay. All right. Okay. So recall about shifts. So and okay. Oops, what happened? Why it doesn't work? Wait, it's because of battery? How can I check the, there's still 20%, should be fine.
Yes, but maybe, let's see what happened.
Oh,
maybe, sorry.
I can use my, I do
Yeah,
have
I think
another.
it should be okay. Well, just maybe.
How about use it? The other, does,
Okay.
does it work, or can it connect to, or maybe no?
Let's see.
Disconnect the previous one.
Yeah. Well, sorry about this. Or we can just wait a while and then. Maybe you can talk a little bit and then. I don't know. Well, what?
Or is it any questions or whatever?
1%.
1%. It probably it will take. I think it
takes the same time, but yeah.
If
Or
you can,
wanna...
yeah, just
Okay,
disconnect.
maybe while you're answering possible questions from the audience, I can try to disconnect and forget it.
Does it work? Can you connect it?
Text accessory, is this it? No, that's the iPhone. Yeah, maybe you can. Somehow it doesn't find it.
It doesn't find it?
Yeah, I don't know why.
Or maybe I just...
Yeah, maybe or should we try to go back to this guy and see what happens? This one somehow connects well, but yeah, maybe.
Or maybe I use connect to my...
Yeah, I don't know. Well, I think we can survive. Maybe whenever you're not using it, maybe when you're explaining, you just recharge a little bit in between, then probably we can survive.
Okay.
Yeah. So sorry about
yeah,
I should
sorry.
have charged it.
So,
We can survive. We'll see.
yeah, I think now we have 3%. So we can write a little bit.
Then, yeah, if we charge in between.
So, okay. So what is this? This was introduced last week. Kind of, but actually for the purpose of later on to compute trees, I need to introduce in a slightly more complicated, add more structure. So this is actually a kind of three-functor formalism, if you like. So from the category perfect pre-stack, this is to the I'll call linear category. This is also was denoted by a presentable one, which are categories that are what we said. This category of linear, stable, infinitive categories with functors being admits continuous right adjoint. And then this is actually not everything, but this, let me write it. This V and all is kind of something is like sending a correspondence, like written in this way. For I write V as a vertical map from Z to X. So this is for such diagram you can associate a bunch of functors, this star pullback and the shrink star push forward and shrink pullback from the category of shifts on Y to the category of the shifts on X, and V is a certain type of morphisms you can construct very general, but it at least contains the so-called proper morphism, which is sort of something. Actually, I need a slightly more in the perfectly finite presented morphisms. This is something that's enough for our purpose, but it contains more morphisms. You can do star push forward. And this construction was via two-stage procedure. It's kind of the first is you start from some usual finite type situation, like for finite type, let's say algebraic space. For some technical reason, why it needs algebraic space to start with, not just the schemes. Then you can, yeah, I think there's nothing needed. So there's a usual L-lattice shift to linear cat. This is a usual. Maybe I don't know what's the people could usual or not. X go to the incompletion of the bounded derived category of L-lattice shifts on X. So that's some kind of thing, at least kind of well understood for a while. It's, I think at least when, it's kind of this DBCX lambda is really what the Lin introduced when doing wave 2. But, and then the first thing is do left can extension procedure. So to go to category of all quasi-compact, quasi-separated algebraic space. But now you allow push forward only in those finite presented ones. You allow star push forward, and then pullback is going to be shrink pullback. So there was actually also, if you just consider pullback, it was already mentioned, discussed in last week in Minja's talk. But you can do a little bit better to also remember the push forward, and you do all possible star push along as soon as it's along finite presented push forward. Then it's okay. And the left can extension, this step is kind of, in other words, roughly speaking, is if you have some algebraic space, you can quasi-compact, quasi-separated, you can write it as an inverse limit of finite type algebraic space. And the shifts on this infinite dimensional thing is always obtained, at least constructible shifts are obtained by star pullback or shrink pullback from some finite dimensional thing. And then you do, that gives this one, and then you do the right can extension to the category of correspondences over all pre-stacks. But now you, okay. To in the finite presented morphism, you allow all push forward. This is what we call shift. The second step is, in other words, is if you have arbitrary stack, pre-stack, shifts on it will be a coherent collection of shifts on each spec A mapped to it, compatible under shrink pullback. And actually you can, that was actually defined last week by Minja, but you can do better. Instead of just, not just remember pullback, shrink pullback, but you can remember push forward along certain morphisms. And this is, in particular, you can remember the push forward along the so-called infinite presented morphisms. That is just, so these are like F is, yeah, maybe I should say it here, because I already mentioned this, what are these infinite morphisms. So this F, this contains F from X to Y, so-called in the finite presented. If F itself can be written as, X can be written as a direct limit of Xi to Yi. So this Xi to Y is the finite presented. And the transition maps are close embedding. Okay, so that's a definition, and so you can do star push forward.
Do you require this sort of after pulling back along a random test map?
Huh?
Do you really want the morphism to have this structure, or only after like testing along a random map from an affine scheme?
Yes, that's right. You need to, that's right. For every, yeah, you're right. How should I say that? If for every, I should write is y prime to y x f prime diagram, like Cartesian diagram like that, x prime can be written in this way. With y, let's say y affine, or algebraic space. Yeah, this is what you really need. Thank you. Right, so you can do, so the second CAN extension is not that easy because you're doing CAN extension along a non-full embedding. So it requires some work to, so this is okay, but it's okay. But how do we work with it? So this is, I want to see that this is, so in this formalism, it's always you have basically start push pull back and the shrink pull, start push forward and shrink pull back. But one thing we already, how to work with it is if X, let's see, I want to say three things, but if I have enough time, if not, I'll continue this afternoon. The first thing is if X is just quasi-compact, quasi-separated, then this category itself is compactly generated. This is an easy observation. Facts, maybe you write this. Because X, this is because X can be written as an inverse limit of finite type thing. So then shifts on X is just co-limits of shifts on Xi. And each one is by definition incompletion of constructible shifts. So it's by definition compact generated. And if you have a co-limit of category of compact generated category, the co-limit is compact generated. Yes, question? X is an edge break, a quasi-compact edge break space.
And transition maps in the co-limit are lower shriek?
Transition maps are upper shriek. Yeah, this was, I think Minja mentioned this definition, this first, this is like, this one to CAN extensions. Yeah, here's the three functor, yeah, I should say here the three functor formalism is already given by shrink pullback and a start push forward. Yeah, it's okay. So the crucial thing is the second is this is first easy observation. The second is really slightly complicated. Is I want to ask the following question: the definition, you know, these are functors, co-limit preserving functors, sort of by definition. It will automatically has right adjoint, although the right adjoint may not, let's say, preserve, may not be co-limit preserving. But it's more, sometimes it's important to ask whether there exists left adjoint functor. So this is some questions. And if you look at the theorem, actually, by the way, this actually already, when you discuss this shift theory, it already explains in this whole formalism, these functors are defined. Okay, in this theorem, because shrink pullback are always defined, and start push forward are defined for finite presented morphisms. And this one of the geometric factors we said is I and the J are finite presented, so they're defined. But in this theorem, it also says there's when this lower star and the upper shrink has left adjoint sometimes, and so you were asking, then you want to ask whether these left adjoint functors are defined. So I want to ask, sort of maybe discuss a little bit about when left adjoint exists. And it doesn't exist, it doesn't always exist, and if it exists, there's some reason. So, but I want to, this is also a good, I think, to explain this is, I would explain it by explain in some special example why when they exist, and it's also give you some idea how to work with this kind of category of shifts, because so far the definition is very abstract, but maybe want to try to see when the left adjoint exists, you can get a little bit idea how to understand it. So now suppose I have just think about the x to y. This is a morphism of a quasi-compact, quasi-separated algebraic spaces. So I want to ask when, let's say, let's say F is, let's say, finite presented. And I want to ask when the left adjoint exists. Let's say we have the star push forward. Then I want to ask whether there's star pullback. This is kind of a thing you can ask whether it exists or not. I think it doesn't always exist, but there's a very important spatial situation it does. So recall that every such morphism it's come from sort of, because the finite presented by Northern approximation, it comes from the pullback of finite stage morphism. So you can, you always have this kind of Cartesian diagram with x alpha. These are like, let's see, this is finite presented over little k. And let me write this, just this map is G alpha beta, this is H alpha beta. So, okay, so what we always have, by definition, we always have, let's say, we can do two situations, F upper shrink, pullback. This is, so by the, we always have this. Oops. Okay, by composition of functors, and then by a junction that gives the so-called Bake-Chevalier maps, actually gives us this. If let's say if I want to look at the left adjoint of upper shrink pullback, so what you will get is F. Oh, oops. Which we know they do exist in a finite dimensional situation. This is like in a finite dimensional situation, this is full six-functor formalism. So we have this. I hope I'm doing something correct. H upper shrink, yeah. So we always get this. This is by a junction. This is so-called Bake-Chevalier map. And if it's a G alpha beta is so-called cohomologically smooth, this is an isomorphism. And then if such functor at each stage admits upper shrink, at each finite stage admits left adjoint, and they are compatible with each other, then at the limit infinite stage, there exists the left, this shrink pullback will exist left adjoint given by shrink push forward. So therefore, this leads to the following definition. So people, X, some algebraic space is called, maybe called a standard placid. If X can be written as a inverse limit with X finite type and the transition map, let's say affine smooth, will be cohomologically smooth for all the transition maps. So in this case, what I'm at least illustrate you is this implies that if F is X to Y is a finite presented morphism, I mean, this is a kind of lemma that illustrates a proof between standard placid space then F upper shrink admits a left adjoint. F lower shrink. Okay, so this is kind of thing. Similarly, in fact, F lower star admits a left adjoint given by F upper star. Okay, so it's just completely the same argument. Yes, question?
The previous diagram with this G alpha beta and H alpha beta, we don't need anything on H alpha beta,
Just on G, but it's because it's Cartesian. It's Cartesian, yeah. So actually, what you give this gives you slightly stronger is as soon as Y is a standard placid, F is a finite presented, X is automatic standard placid, and you have such thing. So similarly, you also have a left adjoint for F lower star. It's by the same type of argument. So I'm not going to repeat this kind of argument, but it's always this case. For example, in this theorem, when we talk about the existence of left adjoint of upper, the existence of these two functors, I mean, it does not give automatically from the like three functor formalism, but because all these shifts are built from limit and co-limit in various stages. It will be slightly complex stage. It's limited. There's some limit, co-limit, but at each stage, if you could show all this functor at each stage admits left adjoint and satisfying this base change thing, you can pass to the limit and see this left adjoint exists and deduce what you want. So this is basically the idea of, for example, how this works. I hope I gave you some illustration of how to work with this kind of category of shifts. So I think my time is almost over, but let me just say one more thing before then in the afternoon I will see how to get the kind of illustrate the proof of the theorem. So this is 1, 2, 3. And the third fact is suppose X is standard placid acted by some H is some let's say pro-algebraic group. So affine pro-algebraic group. And suppose, like in the practice, this will be the positive loop group, L plus of something. Suppose this the pro-unipotent radical inside the H is of finite codimension. So the quotient is a really finite dimensional variety. Then is a finite dimensional group. Then the fact is, first of all, this category is compactly generated. And there exists self-duality. Okay, so maybe take 2 more minutes to finish this part. Okay, so idea is you use descent. To write shifts x more h is a limit of shifts on x go to shifts on x times h go to blah blah blah. This is the usual some kind of the descent works in this situation. You need a little bit proof, but now this is a shrink pullback. Descent, but then Now the whole point is if the pro-unipotent radical is finite codimensional, so using this argument I mentioned before, this Schrick pullback admits left adjoints. So you can rewrite this as a colimit diagram using Schrick pullback push forward. This is part of this Lurie's trick to rewrite. If you can pass to the left adjoint, then the limit diagram of categories become co-limit. Yes. The other way, you're right. So this is, but the existence of Schrick left adjoint is just what I said before, like this kind of type of argument. And now it's again a co-limit of a compact generated category. So therefore it's compact generated. This shows this compact generation. And also each one, one needs to do a little bit more work, but in each one, term in this simplicial, these are so-called placid space. So there's some kind of vertical duality coming from the finite dimensional situation. So each term has some self-duality, and this self-duality can pass to the co-limit to get the self-duality. But there involves some choice. One needs to be a little bit careful. But that gives this statement. And maybe in the afternoon, beginning, I'll very briefly explain how to start from this such thing to get the part of the theorem I mentioned. Okay, so I stop here.